Hello there, this is Abdullateef Jamal. I am a final year PhD student at the University of Bradford, and this is my presentation, which is comparing the aerosol in vitro performance and the surface energetics of dry powder inhaler formulations. Many studies on lung deposition have failed to include surface energy calculations to help explain the performance of some of the formulations on the market. Of course, surface energetics play a key role in the delivery of a dry powder inhaler, as there must be a sufficient balance of adhesive and cohesive forces to allow for optimal lung delivery. In this study, the use of inverse gas chromatography and the next generation impactor has established a link between these two aspects. The results allow for an estimation of dry powder inhaler performance based on the surface energetics of the drug and the carrier. Many acid-base models have been developed to characterize the surface energy of solids using inverse gas chromatography. Some of these are the Doris-Gray equation, the Schultz equation, and the Fox equation. So to simplify and unify all these models together, Mohammed has combined all of these to create a chromatographic adhesion law. This is an equation which relies, of course, on IGC data, allows for the calculation of all the intermolecular forces such as the electron acceptor component and the donor component of the solid surface, and it aims to be the most universal method and the most accurate for calculating the levels of adhesion and cohesion for any dry powder inhaler formulation. The aim of the study was to measure the lung deposition of different DPI formulations and the surface energies of the individual formulations. The lung deposition was to be measured using a next generation impactor by running the samples through HPLC. Two different devices were chosen for the inhalers. These were the Aerolizer with the low resistance and the Spiriva hand inhaler which has a high resistance. The chosen API was Budesonide, and the formulations were prepared using two different carriers, these being Mannitol and Lactose, in different ratios. The surface energies were then measured using inverse gas chromatography and calculated using the method proposed by Mohammed described in the previous slide. This study used different ratios of drug to carrier, as many current market dry powder inhalers have different levels of carrier in their formulations. Examples of current market DPIs include the Symbicort Turbohaler, which delivers 1 mg of lactose per delivered dose, the Bufamix Easyhaler, which delivers 4 to 8, and the Budesonide Novolizer, which delivers 11 mg of lactose per delivered dose. All of these inhalers use budesonide as their active pharmaceutical ingredient. For the powder mixing stage, the ratio selected was the 1 to 67.5. This is the same as commercially available Ventolin inhaler. Three different powder mixing techniques were used, the first one being the vortex mixer at the highest speed possible for the machine. The next was the ball mill, also using the highest frequency for that machine, and the final one being the turbulent mixer, used at mid-speed. The results showed that the vortex mixer at 5 minutes provided the best RSD overall based on 10 readings taken, and so this was used for all remaining ratios of drug and carrier. After powder mixing was complete, the powder was then filled into capsules ready for next generation impactor. The first inhaler used was the Aerolizer, and the first mixture used was the Budesonide and Mannitol mixture in 4 different ratios, 1 to 10, 1 to 20, 1 to 40, and 1 to 67.5. As can be seen from the results, the 1 to 10 ratio showed the highest fine particle fraction for this set of formulations, with the 1 to 67.5 showing the lowest fine particle fraction. Moving on to the budesonide and lactose mixtures in the same ratios, again a similar trend can be seen. The 1 to 10 ratio showed a 23.26% fine particle fraction compared to the 20.62% fine particle fraction for the 1 to 67.5 ratio. This means that the 1 to 10 ratio for both budesonide lactose and budesonide mannitol showed the highest fine particle fraction when using the Aerolizer inhaler. For this next set of results, the inhaler was switched out for the Spiriva inhaler and a different budesonide was introduced. The original was Budesonide X with 1.52 micrometers, whereas Budesonide Y had a slightly larger particle size of 3.15 micrometers. If we look at the Budesonide X results first, the 1 to 10 ratios showed a very high fine particle fraction for both Budesonide Mannitol and Budesonide and Lactose when using the Spiriva inhaler. This coincides with what we saw with the Aerolizer inhaler previously. The next and final step was to run the powder formulations using inverse gas chromatography in order to calculate the work of adhesion and the work of cohesion, using the methods proposed by Muhammad in the previous slides. By creating a ratio of work of adhesion over work of cohesion, it's possible to compare the results of every set of formulations to see which one is the highest. If we look at the first set of data, which is the Budesonide and Mannitol, we can see that the 1 to 10 ratio has the highest ratio of adhesion over cohesion for that set of formulations. And if we look at Budesonide and Lactose below them, the same can be seen, where the 1 to 10 ratio of Budesonide and Lactose also has the highest ratio of adhesion over cohesion for that set of formulations. This means that it's possible to estimate the FPF formulations based on the IGC results, where we can see that the higher ratio of adhesion over cohesion correlates with the higher FPF seen in the NGI. In other words, the higher the ratio of adhesion to cohesion, the higher the FPF seen in the NGI. In conclusion, the low performance of many current market formulations for lung inhalation highlight a key aspect for future research. Many of these formulations provide less than 50% fine particle fraction, which is resulting in a lot of medicine wastage. There are many studies that have been done on lung deposition and surface energetics, but they have been rarely done together to help counteract each other and explain the results of one another. By measuring the surface energies of a set of formulations using inverse gas chromatography and comparing these to their lung deposition using an NGI, it's possible to identify the best ratio of drug to carrier for that set of formulations that will provide the most efficient lung deposition and formulation performance. Thank you very much for listening.